Hello people, welcome one and all to Jojo's Learning Club.
So hello guys, welcome back to my channel Jojo's Learning Club. So this is the part 3 on electronic device circuits, and on this section I'll start with the current and about diffusion current, drift current and so on. In the last sections, if you wanted to see videos, just go to my channel and you can see from the videos part 1 and part 2 if you wanted to get a continuation on the whole basics of electronic device circuits, or just if you wanted to just know something about it, just start with this video. And this video will start with current, diffusion current and drift current exactly. So for that, first let's understand what is a current. Current is defined as the rate of change of charge, which is I equal to dq by dt, rate of change of charge. That is called a current, and it is represented in ampere. In a semiconductor there is a bipolar current, while in metal it is unipolar. In semiconductor there is a bipolar current, that is current is carried by both electrons and holes. So first let's understand what is a drift current. Drift current means it is a flow of current through the material or device under the influence of field intensity or applied voltage. So what is drift current? It is a flow of current through the material or device under the influence of electric field or a applied voltage. So voltage, driving force, and you get drift current. So without applying force or voltage, what kind of current you get? Diffusion current. That's what you have to understand for now. And we can see the operating temperature. For germanium it is minus 60 degree to plus 75 degrees Celsius. So the maximum operating temperature is 75 degrees Celsius. So for silicon it is minus 60 to 175 degrees Celsius. So the maximum operating temperature is 175 degrees Celsius. So silicon is more suitable for high temperature application. So you can see now one of the more options why we are using silicon. Normal working temperature. For semiconductor devices, the normal working temperature will be less than or equal to 400 Kelvin. So above 400 Kelvin, what happens? The property changes and comes into material science. That's why whenever we deal with semiconductors, the normal working temperature will be less than or equal to 400 Kelvin. And now let's understand why carbon is not considered as a semiconductor element. In periodic table, group 4, see carbon is also included like silicon and germanium. But we don't use carbon as much more use. There are some reasons behind it. Energy gap of carbon is very less, has unstable, unreliable and unpredictable properties. Sometimes see a carbon is used as a conductor, for example in terms of graphite, and sometimes a carbon is used as an insulator in terms of diamond. Okay, so now let's go back to the leakage current IO. So it is also called minority carrier current or thermally generated current or reverse saturation current. Leakage current actually depends on the minority carriers, and the minority carrier concentration depends on temperature, and therefore this current is generated because of temperature. So therefore it is also called what? A thermally generated current. So leakage current depends on minority carriers and minority carrier concentration. It depends on temperature, and therefore this current is generated because of temperature. Therefore it is a thermally generated current. If leakage current are small, then what happens? The temperature effect on the material or device is less, because less leakage current when there is temperature is less, and this indicates better thermal stability. Sorry, if a leakage current are small, then the temperature effect on the material or device will be less. That's what I wanted to mean. And if the temperature is actually not too much dependent upon the leakage current, then you can say that this material is having a better thermal stability. And IO is what is IO, or the leakage current. It is like mu microampere for germanium and nanoamperes for silicon. So this is one of the other reasons why silicon is preferred more when compared to germanium. See, the leakage current for germanium is in terms of microampere. It is huge when compared to silicon, which is just nanoamperes. Silicon is having better thermal stability than germanium due to smaller leakage current. Right, that is why we use silicon more. You can see most of the materials in the semiconductor fields are made up of silicon when compared to the germanium, and this is one of the main reason because the thermal stability for silicon is much higher, and also you saw right, it can withstand more. Maximum operating temperature is around 175 degrees Celsius when compared to germanium, which is having only 75 degrees Celsius. Leakage current is independent of applied voltage. That is, a current is saturated with respect to applied voltage, and hence the name saturation current. Leakage current is highly sensitive to temperature. That's all about now for the leakage current, and our next topic will be resistivity. So what is actually this resistivity? The resistivity is a property that describes the extent to which a material opposes the flow of electric current through it. So it is just an opposition for the flow of electric current through it, and its unit is ohm centimeter or ohm meter. So for metals, it is having a positive temperature coefficient of resistance. That is, resistance increases with increase in temperature. As you know, the formula R is equal to rho L by A. That is for resistivity. I am not describing this in more because you have already learned about it, and this is just we are dealing with electronic device circuits, and it is known that should have a basics about this. So in metals, the resistivity increases with increase in temperature. For semiconductors, negative temperature coefficient of resistance, that is, the resistance decreases with increase in temperature. In semiconductors, when the resistance decreases, what happens? So the resistivity is also decreases because R is directly proportional to the resistivity rho. So resistivity decreases with increase in temperature. So that's about resistivity. And now let's learn what is conductivity. Conductivity is what actually it is a reciprocal of resistivity. Sorry, it is a reciprocal of resistivity. And it here so in resistivity, what it was is it was actually an opposition to the flow of current, right? And conductivity denotes current carrying capacity, just the opposite of it. So if you learn resistivity, you can also understand conductivity, right? So unit of resistivity was ohm centimeter, and here it is 1 by ohm centimeter, or is mho per centimeter or mho per meter. Conductivity is called depends on three factors, that are carrier concentration, charge, and mobility. Variation in conductivity due to temperature depends on variation in mobility of charge carriers, variation in carrier concentration. So for metals, it is unipolar. We said what are the all factors? Carrier concentration, charge, and mobility. So conductivity sigma is dependent on charge N, carrier charge Q, sorry, carrier concentration N, and mobility mu N. So in metal, conductivity decreases with increase in temperature. In metal, free electrons is independent of temperature. In metals, as temperature increases, mobility of charge carrier decreases, and therefore conductivity decreases. So what happens actually when temperature increases? The mobility of charge carrier decreases, and because of that, what? Conductivity decreases. For semiconductors, it is bipolar. So it is not just made of electrons, it is made up of electrons and holes. So you have to consider the both sides. N into Q into mu N, which is the conductivity due to electrons, and P into Q into mu P, which is the conductivity due to of holes. In a semiconductor, the conductivity increases with increase in temperature. So you know that, right? Conductivity, mobility decreases, but there is some other factors which contribute. We are going to discuss about that. In a semiconductor, as temperature increases, the mobility of charge carrier decreases, like in metals, and it will reduce the conductivity slightly, but it also reduces the conductivity. And at the same time, what contributes? Because of the temperature, a large number of covalent bond will be broken. So what about covalent bond, you will learn later. So just for the time being, understand that the same time, because of temperature, what happens? A large number of covalent bonds will be broken, and large number of electrons and holes are created. And because of the covalent bond brokening, there will be large number of electrons and holes which are created, and this will increase the conductivity, and hence the net result, conductivity increases with temperature. So that's what happens in case of a semiconductor. In a semiconductor, conductivity mainly depends on carrier concentration because of the forms of electrons and holes. Okay, semiconductor means by default we are using this semiconductor, it actually means whenever we are using a semiconductor, it means by default it is an intrinsic semiconductor. So what is an intrinsic semiconductor will be discussed on the later section on detail. So whenever a semiconductor is said, it is by default it is meant as intrinsic semiconductor. Okay, and on the next topic we are going to deal with the current density. It is the current passing per unit area. So what is current density? It is the current passing per unit area, and it is denoted by J, and J is equal to I by A, which is equal to ampere per meter square, or in other terms of I you can write as sigma into epsilon ampere per meter square. So the unit is ohm per meter into volt per meter. Ohm per meter is mho into volt. Okay, for metals, J is equal to N into Q. You substituted, it is sigma into epsilon, right? Sigma, you already know that it is N into Q into mu and epsilon. So for metals, it is just by one. You can see current density is only by the electrons, and so N into Q into mu and into epsilon. But in case of semiconductor, it is N into Q into mu n plus P into Q into mu P, the whole brackets into epsilon ampere per centimeter square. Okay, now let's understand about the conductivity sensitivity. In intrinsic semiconductors, conductivity increases with increase in temperature. So for 1 degree Celsius, conductivity of germanium increases by 6%. For 1 degree of silicon, conductivity increases by 1 degree Celsius. The conductivity of silicon increases by 8%. Actually, there is a relation which we will learn it later. So when compared to germanium, the conductivity of silicon is more sensitive to temperature, right? You can see that by the relation here. So when compared to germanium, conductivity of silicon is more sensitive to temperature, but silicon is more suitable for high temperature application. Why even then conductivity is like more sensitive to temperature, we prefer silicon over germanium. Why? Because you saw in the earlier video or in the earlier section that, see, the leakage current, it was in terms of microampere, which is a major contribution in terms of germanium, and in the terms of silicon it was just nanoamperes. So there is a huge difference in the terms of the leakage current, and that is why silicon is more suitable for high temperature applications. With this, I'm concluding for the video for today's video, and on the next section we'll deal with the energy gap, and then we'll give a brief introduction into semiconductors. So that's all for today's video. Thank you and have a nice day.